Hello, quick video on expectation algebra and how we use it for continuous random variables. As we've looked at for discrete, we may want to create a new random variable z here, which is made up of x and y, when added together, or x minus y, where x and y are independent variables, or in its most general terms, where z is some multiple of x plus or minus some multiple of y. So I'm going to go through and do the algebra to prove our standard results. Okay, so let's consider a z, which is a x plus or minus a by. Yep. So if we therefore want to find our expectation of that, we just need to find our expectation of this expression here, ax plus or minus by. And in the world that we're working in continuous, if we've got two variables, we've effectively got to work out what our z value is, there it is, multiply it by our probability of the x and y values that we're interested in, and then integrate it over the whole range of values of x and y between their minimum values and their maximum values. So in effect, we've got our surface here, because we're going over all the ranges of x's and y's, and effectively our z value is our vertical here, and we're going to integrate the volume under the surface we do it for particular x and y values, but here we're integrating it across the whole range. Yep. So the probability underneath this surface should in total be 1, shouldn't it? And here we're going to find the expectation by multiplying those probabilities by our z value. Now, the important thing now is to deal with this intersection here, the probability of x intersection y. We need to simplify that. And we're going to do that by assuming independence between x and y, and therefore we can replace the probability of x and y with the probability of x times multiplied by the probability of y, and that's what I've written here. So px is the probability of a particular x value, and py is the probability of any particular y value. Okay, so if I put that into my integral, I've got my z value again here, and it's multiplied by p of x, multiplied by p of y, and then integrated over the range dx dy from max to min to max there. Yeah. Now, what we're going to do is a bit like we did with the discretes, we're going to split this up. And we can split this bracket here into two parts, and we'll get two integrals. So the first integral is going to be with our ax multiple, and our second integral is going to be with our by multiple. And in the middle here we have our plus or minus, don't we, to tell us what we're going to do with these two integrals. Okay, I'm going to follow the left-hand integral down and try and work it out and show our answer to that. So let me just move it up slightly so we can see it. So our left-hand integral inside a bracket here, inside our integral we had, it's a multiple of ax times our probabilities, yeah? Multiplied by our probabilities. Now a is a constant, so we can move that out front as we do in all integration. So now we've got an integral with our px inside it. Second part that's interesting is we have py inside our x integral, but py is not a function of x. So so therefore it's effectively a constant within that integral, and so I can move it outside of my integral with respect to x. So there you are. I can see I've rearranged this here, changed the order. So at the back I've got a py dy. Now I can't, as I did with the a, move the py right outside of the integral, because actually py is a function of y, so it has to stay in the y integral. Okay. But as a result of moving it, I am left with this integral here in x px, all integrated dx. There's no y's in there, it's just a function of x, and we probably recognize that expression there to be the expected value of x. There we are. So tick, we've got that simplified. But then our next step is to think about the fact that that expected value of x is inside our y integral. But of course, it's not a function of y at all. So effectively, for the purpose of the integral, it's a constant, and therefore we can move it out the front as we did with the a. We can take it outside the integral. So now I've got an a times multiplying ex, and then my integral of py dy over the full range of values of y. And we can recognize that the total probability over the full range in any probability distribution is 1. So I'm left on the left hand side with a multiplied by expectation of x multiplied by 1, and that gives us our first term in our standard relation, isn't it, which is basically a e expectation of x. Okay, let's go and do our second term here, and this is our second integral, and we moved our, and this is the integral, the plus or minus the by multiplied by probability of x, probability of y, and then integrated dx dy. So as we did with the a's, we can see that the b is a constant. We can move that out of the front. We're now left with an integral, and the second part this time is that our py again is not a function of x, so we can move that out of the x integral, leave it in the y integral. But we've also got this y here, and that's not a function of x, so we can move that outside the x integral, but leave it inside the y integral. At this point, in this order, we can see we have an inner integral here in x, which is basically the integral of px dx. And over the full range, we know that the total probability under the x is 1. So that's 1 there, which is effectively 1 times something. Well, that effectively is unity, so it just disappears out of our calculation now, which means we're left with this integral on the right hand side, which is y times the probability of y dy, which we can recognize to being the expected value of y, and that of course is multiplied by the b we brought out the front. And therefore we've got our second term here, which is plus, so we've got our overall expectation is a times expectation of x plus or minus b times the expectation of y. So can you see how we broke this integral up in this case from one integral into 2 integrals in order to get our solution here? Okay, let's move on then. We found our expected value. Now let's have a look at what our variance is. The first thing we need to find our variance is we're going to have to find our expected value of z squared. Well, we know what z is, so z squared is just that bracket squared, and then we're multiplying it by the 2 probabilities again, and then we're integrating it over x and y. If we expand this bracket this time, we get 3 terms. We get a squared x squared plus or minus abxy and b squared y squared. And we're going to find the same trick as we did before. We're going to split it into 3 separate integrals, and we'll work each of those through. So let's do the first one. Our first integral here, we're going to take off our a squared x squared. Well, a squared is going to be a constant, so that can go outside the integral, and I've got x squared px py integrated dx dy. And as we did before, py is not a function of dx, so we can take of x, so we can move it outside the x integral. So we've got a py dy at the right hand end. That means that inside the inside integral now is just x squared px dx, all function with respect to x. They're all functions of x, and we can recognize that that's the definition of the expected value of x squared. And once again, the expected value of x squared is not a function of y, so that can come outside the integral as a multiplier, and therefore we end up with a squared expected value of x squared, and then the integral of py dy over the full range, which we know to be 1. And therefore our first term becomes, our first integral simplifies to a squared times the expectation of x squared. That's our first term. Let's have a look at the middle term. Do that one in blue. So here was our middle term was plus or minus 2abxy, and we're going to turn that into an integral here. Now our 2ab is a constant, our xy isn't a constant, so that stays inside our integral. And our next step then is to tidy up this integral. Well, as we've done before, we can move our y term here and our py term outside the x integral. There we go, so I'm going to put them there, which means that I'm just left with this integral here as a function of x times px dx integrated, which we can recognize again as being the expected value of x, which of course is not a function of y, so can therefore come outside the integral. So I've now got 2ab multiplied by e to the x and the integral of y py dy over the full range, which we recognize to be expectation of y. So therefore our middle term is going to be 2ab times the expectation of x times the expectation of y. So that's dealt with our middle term. Now let's go to our third term. It's going to be very much like our first term. We had our first integral, so we had our b squared y squared, and in that integral, that's our third integral. Our y squared therefore is coming inside of our integral, but the b squared is a constant, therefore can come outside as a multiplier. And again, if we start changing the order, we can move our py outside of the dx integral because it's a constant in effect, and we can move our y squared outside the x integral, again because it's just a constant, it's not a function of x. So now we're left with the x integral, the integral of px dx, which we can see is the sum of all the probabilities dx, which is going to be 1. So that's 1, which effectively is unity, so it just disappears. Let's just multiply that, and therefore we're left with this integral here on the right hand side, y squared py, which we will recognize to be the expectation of y squared. And of course that's multiplied by b squared on the outside and the front. That's our third integral, then simplifies to b squared expectation of y squared. Yeah. So here we have our three terms that we've just worked through for our expected value of z squared. Okay. Now we need to find our variance. So our variance is our expected value of z squared, which we found here. That's what we've just calculated there, and I've done in the orange. And then we've got to subtract from it our expected value of z all squared. Now we've calculated, we've got a formula for the expected value of z, haven't we, from our first part, and there it is. And we're just going to square that. So if we do that and expand the bracket, then we get that in green. And then if we have a look above, between the orange and the green, we can see that our first two terms purely relate to x. So if we group those together, we see they've both got a squared as a factor, and we've got the expected expectation of x squared, and then we're subtracting from it the expected value of x squared, which we'll recognize as being variance of x. And similarly, if we take our final two terms here, we can see that we pull those together, we've got b squared times the variance of y. Now, what happens to these terms in the middle? We can see that actually we're subtracting one from the other, and they're exactly the same. Therefore, they're going to cancel out. So we don't get that term in the middle, and therefore, as a result, we've got to our conclusion that the variance of ax plus by is going to be equal to a squared times the variance of x plus b squared times the variance of y. So there we have it. Quick summary. if we've got a combined continuous random variable z, which is a linear combination of x and y, and that these two variables are independent, we can therefore write our probability in the form px times py, and therefore we can calculate, we can prove that those are going to be the expectations. And that's really useful because it will help our expectations of variance other, and that's going to really help us for when we get on to combining normal distributions, which is in a separate video. Hope that's of use.